Welcome to Fun Facts Online. Today, we are stripping away the noise of the universe to look at one of the most significant breakthroughs in modern physics, a discovery that happened late in 2025 and involves one of the most tangible materials on Earth, the diamond. In the quiet, dust-free sanctuaries of modern physics laboratories, a revolution has been brewing, one that promises to render the invisible visible. For decades, our ability to measure the world has been fundamentally constrained by the laws of classical physics. We have effectively been like astronomers, trying to study distant stars through a foggy lens, limited by the inherent noise of the universe itself. But recently, the fog began to lift. Researchers have unlocked a new frontier in measurement technology by harnessing the strange, counterintuitive properties of quantum mechanics within synthetic diamonds. This is the story of quantum squeezing, a technique that allows scientists to effectively cheat the classical limits of measurement. We are going to explore how a specific defect in these diamonds, known as the nitrogen-vacancy center, has become the engine for a new generation of sensors. These aren't just incrementally better sensors. We are talking about a paradigm shift capable of detecting the firing of a single neuron, mapping the magnetic field of Earth's crust for unjammable navigation, and peering into the atomic structure of superconductors under pressures found at the center of the Earth. To understand the magnitude of this breakthrough, we first need to understand the barrier that has held us back for so long, something physicists call the standard quantum limit. Every measurement you have ever made is essentially a conversation between the observer and the observed. When you use a ruler to measure a table, the interaction is simple and static. But when you try to measure the magnetic field of a single electron or the gravitational pull of a tiny mass, the act of measuring becomes incredibly messy. At the quantum scale, nothing is ever truly still. Particles jitter, energy fluctuates, and the vacuum of space itself hums with activity. In classical sensors, this manifests as something called shot noise. Imagine trying to determine the average position of a crowd of people by taking a single snapshot. If the people are moving randomly, your snapshot will always have a degree of blur. In the quantum world, this blur is fundamental. According to Heisenberg's uncertainty principle, you cannot perfectly know both the position and momentum of a particle, or in the case of sensors, the amplitude and phase of a signal, with infinite precision simultaneously. For decades, the standard quantum limit was the practical ceiling. It dictates that the precision of a measurement scales with the square root of the number of particles used in the sensor. This is a harsh law of diminishing returns. To get twice the precision, you need 4 times as many sensing particles. To get 10 times the precision, you need 100 times as many. This scaling law is exactly why ultra-precise sensors have traditionally been massive, power-hungry, and expensive. Before the diamond revolution, humanity's best attempts to touch the quantum floor relied on bulky, fragile technologies. We had SQIDs, or superconducting quantum interference devices. These are the heavy weights of magnetic sensing, capable of detecting fields as weak as a quadrillionth of a Tesla. However, they have a fatal flaw. They require cryogenic cooling to near absolute zero. This traps them in labs, tethered to liquid helium tanks, making them useless for a portable brain scanner or a navigation chip in a drone. Then we had atomic vapor cell magnetometers, which use a gas of alkali atoms like rubidium to sense magnetic fields. While they can operate at room temperature, they suffer from spatial blurring. The gas atoms move around, averaging out the signal over millimeter scales. They cannot see the fine, nanometer scale details of a biological cell or a microchip. The world needed a sensor that combined the extreme sensitivity of a ski tail, the room temperature operation of a vapor cell, and the microscopic resolution of an electron microscope. The answer lay in a gemstone. Diamond is famous for its hardness and brilliance, but to a quantum physicist, its value lies in its flaws. A pure diamond is a boring lattice of carbon atoms, but if you remove one carbon atom and replace its neighbor with a nitrogen atom. You create a nitrogen vacancy, or NV center. The NV center acts like a single atom frozen in solid ice. Because the diamond lattice is so rigid, it shields this defect from the chaotic vibrations of the outside world. This allows the NV center to maintain its quantum coherence, its fragile quantum state, even at room temperature. This is the holy grail feature that separates diamond from almost every other quantum material. The NV center has an extra electron spin that can be manipulated with microwaves and read out with a simple green laser. If you shine green light on it, the NV center fluoresces red. If you apply a magnetic field, the intensity of that red light changes precisely in response to the field strength. By monitoring the brightness of this red glow, scientists can measure magnetic fields, electric fields, temperature, and strain with incredible precision. But until recently, even NV centers were hit by the standard quantum limit. A single NV center is too noisy. A group of them is better, but they usually act like a crowd of individuals shouting over each other, uncorrelated and chaotic. This brings us to the breakthrough in late 2025. A team of physicists at UC Santa Barbara, led by the group of Ania Jajic, shattered this barrier. For the first time, they successfully engineered a 2D layer of NV centers that were not just shouting individually, but singing in harmony. They achieved this through quantum squeezing. Squeezing is a metaphorical term for redistributing quantum uncertainty. Imagine a balloon filled with air. The air represents the noise or uncertainty in your measurement. You cannot get rid of the air because Heisenberg says the noise must exist, but you can squeeze the balloon. If you squeeze it flat from the top, it bulges out the sides. The height of the balloon represents the uncertainty in the property you want to measure, such as the phase of a magnetic signal. The width of the balloon represents the uncertainty in the property you don't care about, such as the amplitude. By squeezing the quantum state, researchers reduce the noise in the measurement direction, effectively flattening the balloon, while dumping that excess noise into the other direction where it doesn't hurt the measurement. Achieving this in a solid block of diamond is incredibly difficult because the spins of the NV centers naturally want to decohere or lose their connection due to the messy environment of the diamond lattice. The UCSB team developed a novel control pulse sequence called the asymmetric many-body echo. To visualize this, imagine a room full of pendulums representing the spins, all swinging at slightly different rates due to friction and wind. In a standard echo, which is the classical approach used in MRI machines, you pause time, flip all the pendulums upside down, and let them swing back. This cancels out the wind and brings them back to sync. But with the asymmetric many-body echo, the researchers didn't just flip the pendulums. They applied a complex, uneven rhythm of pulses that did two things. First, it canceled the environmental noise. Second, and this is the key, it forced the pendulums to interact with each other. This interaction created entanglement. The spins stopped acting as individuals and started acting as a single, massive quantum object. When one spin felt a magnetic field, they all felt it. This collective behavior amplified the signal, while the noise, which was random for each spin, canceled itself out. The result is a sensor that surpasses the standard quantum limit, scaling its sensitivity not by the square root of the number of particles, but closer to the number of particles itself, approaching the Heisenberg limit. This transition from classical diamond sensors to squeezed diamond sensors is the difference between a magnifying glass and a microscope. This leap in sensitivity, combined with the robustness of diamond, unlocks applications that were previously science fiction. Let's look at medical imaging. The human body is an electrical machine. Every heartbeat, every muscle twitch, and every thought is driven by ionic currents that generate tiny magnetic fields. Currently, detecting the magnetic field of the heart, a process called magnetocardiography, requires a squid room shielded with thick steel walls to block out Earth's magnetic field. Squeezed diamond sensors can potentially do this in a portable device the size of a smartphone. This allows for the detection of heart anomalies, like ischemia, that regular EKGs miss, because EKGs are purely electrical and affected by body tissue conductivity. Then there is magnetoencephalography, or MEG. Mapping the brain's firing patterns usually involves a helmet that looks like a giant hairdryer filled with liquid helium. Diamond sensors could lead to a lightweight cap that allows patients to move naturally, while doctors image their brain activity with neuron-level resolution. This could revolutionize the diagnosis of epilepsy, Alzheimer's, and concussions. Researchers have even grown neurons directly on diamond chips. With squeezed states, they can detect the firing of a single neuron without sticking an electrode inside it, enabling non-invasive, high-speed interfaces between brains and computers. Now, consider navigation. We are dangerously reliant on GPS. A satellite outage or jamming signal could cripple global logistics, but the Earth itself provides a map. The crust of our planet has a unique magnetic fingerprint comprised of local anomalies caused by iron ore deposits and geological structures. A diamond quantum sensor is sensitive enough to read this magnetic map as a plane or ship moves over it. By matching the real-time magnetic reading to a known database, a vehicle can determine its location with meter-level accuracy without ever seeing the sky. Unlike GPS, the magnetic crust cannot be jammed or turned off. Diamond sensors, being small and solid-state, can be integrated into aircraft autopilots and potentially even autonomous cars as a backup navigation system. We also see applications in the microscopic world. In 2025, parallel research at Berkeley Lab utilized nanodiamonds, which is essentially diamond dust, inside microfluidic droplets. Imagine a tiny water droplet acting as a test tube. By putting squeezed nanodiamonds inside, the droplet itself becomes a sensor. These droplets can detect trace amounts of specific ions or molecules. In a bioreactor growing lab-grown meat or pharmaceutical drugs, these sensors could monitor pH and metabolic rates in real time, adjusting the nutrients automatically to optimize growth. One of the most heavy metal applications of these sensors is in high-pressure physics. Scientists squeeze materials between two diamond anvils to simulate the core of Jupiter or create room-temperature superconductors. Because the sensor is a diamond, it can survive the crushing pressure. In late 2025, researchers used NV sensors to measure the magnetic properties of titanium and hydrides at pressures exceeding 240 gigapascals. That is 2.4 million times atmospheric pressure. They observed the Meissner effect, the expulsion of magnetic fields that prove superconductivity, at pressures where no other sensor could survive. This is a critical tool in the race to find a superconductor that works at room temperature and pressure. The shift from academic papers to commercial products is already underway. The Quantum 2030 strategies of nations like Canada and the UK have identified diamond sensing as a critical technology for national security and economic growth. Bosch Quantum Sensing, the German engineering giant, has partnered with Element 6, the synthetic diamond arm of De Beers, to mass-produce diamond quantum sensors. Their goal is a chip-scale magnetometer for the automotive and consumer electronics markets. They envision a future where your phone has a quantum sensor to improve indoor navigation or control interfaces. QNAMI, a Swiss pioneer, produces scanning NV microscopes. These are essentially record players, where the needle is a diamond tip with a single quantum sensor. They are already used by the semiconductor industry to inspect the magnetic memory of next-generation hard drives and chips. The roadmap for this technology is aggressive. By 2026 and 2027, we expect the first commercial prototypes of squeezed sensors for niche scientific markets. By 2028, we anticipate the integration of diamond sensors into industrial monitoring, such as checking for microcracks in steel pipelines, or monitoring electric vehicle battery health by sensing current flows non-invasively. By 2030, The target is the deployment of medical-grade imaging devices in clinics and magnetic navigation systems in defense and aerospace sectors. The future is crystal clear. The breakthrough of quantum squeezing in diamonds is more than just a technical improvement. It is a democratization of quantum power. We are moving away from the era where quantum physics was confined to dilution refrigerators in the basements of universities. We are entering an era where quantum effects are harnessed in a chip at room temperature. As we look forward, the convergence of AI and quantum sensing looms large. Squeezed sensors produce massive amounts of complex data. Artificial intelligence will be the key to interpreting this noise-reduced signal, identifying the subtle magnetic signature of a developing tumor, or the faint geological anomaly that signals a hidden mineral deposit. The standard quantum limit has been breached. The diamond, once a symbol of static, unyielding endurance, has become the most dynamic and sensitive eye we have ever opened onto the universe. We are no longer just looking at the world. Through the squeezed states of a diamond lattice, we are finally seeing it clearly. Thank you for listening to G Fun Facts Online.